Hi, welcome to Moreauknows. Today we're going to be talking about water potential and going over some questions that I gave my AP students in class. If you don't know what water potential is, you might want to go back and check out my previous videos and how to use the water potential equation. This right here is off of the calculation sheet that you will be given during the AP test. And so any of this information you do not need to memorize, but you do need to know how to use it. And that's what I'm going to teach you here today. This lesson is going to build onto every question. And so each question is going to get a little bit harder and a little bit harder. But we're always going to deal with the same thing. We're going to have a cell, and it could be an animal cell or a plant cell, in a solution of water. If a cell's psi p is 3 bars and its psi s, or for solutes, is negative 4.5 bars, what is the resulting psi? Well, I need to know the equation psi, and I'm going to say this is for the cell, is going to be equal to psi p plus psi s. So I still need to find out what psi c is, but for this problem I have psi p as being 3 bars and psi s being negative 4.5 bars. And so if I add those up really quick, the psi of the cell is going to be negative 1.5 bars. And that's how you find the answer. For this next question, we're going to take the cell from number 1, which its bar is negative 1.5, which we just found, is placed in a beaker of sugar water with a psi s equaling negative 4.0 bars. Okay? And then we need to figure out which direction the water would flow. Well, and if a psi s is negative 4.0 bars, it seems like they're not telling us a lot of information, but actually they are. Remember to find the psi of the beaker, so let's just say psi b is going to be equal to the psi s minus the psi p. And so to find the psi of the beaker, of what's in the beaker, we use negative 4.0 bars minus the psi p. Well, what's the psi p? Well, since it's placed on a beaker and we don't really have any pressure besides the atmosphere acting against the surface of the liquid, then the actual pressure that's in bars is going to be 0. So our psi b inside the beaker is going to be negative 4.0. So outside here, it's going to be negative 4.0. And how do you know which direction the water will flow? Well, the water is going to flow to the more negative number. And so it'll always move from a high concentration of water to a lower concentration of water. So if I had negative 5.1 and negative 4, negative 4 is a lower number. And just like I have shown you guys before, they're moving from a high to low with no energy. And so they're going down that concentration gradient. This would also be the same as thinking about numbers in a linear format, where I'd have 2, positive 1, 0, negative 1, negative 2, negative 3, negative 4. I'm moving from a 1.5, which is a higher concentration, to a lower concentration here. So I am still moving down that concentration gradient to a more lower to a lower water potential. I'm still moving to a lower water potential. And so kind of keep this in mind when you're doing the rest of these problems. You're always moving from a higher number to a lower number. So in the end, the water will move out of the cell. What happens if in the original cell from question 1, which was negative 1.5 bars, is placed in a beaker with sugar water with the solute of negative 1.5 bars. And what direction would that flow be? Well, again, remember, if we have the psi of the beaker, and we need to know the psi S plus the psi P, well, the pressure is going to be 0, and we already know that this from the information above is 1.5. So negative 1.5 plus 0, the psi B inside the beaker is going to be negative 1.5. So if there's a negative 1.5 and a negative 1.5 inside and outside of the beaker, what does that mean? Well, water is going to still move from a high to low water potential, but in this case there is none. And so water will move outside the cell and inside the cell at the exact same time. And this will make the cell be at homeostasis, or it is considered to be in an isotonic solution. Okay, so the first part of the question of this next new problem says the value for psi in a root tissue was found to be negative 3.3 bars. And so if I wanted to make this cell a plant cell, I could add some chloroplast and put a cell wall around this animal cell, and that's going to be our plant cell for now. Just work with me. And the total psi is going to be negative 3.3. And then it says if you take the root tissue and place it inside a 1 molar solution of sucrose at 20 degrees Celsius in an open beaker, what is the total psi of the solution, and in which direction would the net flow of the water be? So for this, I'm going to go back to white. We need to know how to figure out what all this stuff, how we can work with this stuff. And so the first thing we're going to need to find out is the psi S. And that has a cool little equation called negative I CRT. And the way that we're going to find out what psi S is by taking that negative I, and I is going to be the ionization constant for sucrose, which is just 1. If it was salt, it would be 2, and that's pretty much all you're going to be working with. And then our concentration, which is going to be 0.1 molar. And then our R is our constant, so that's 0.0831 liters per bar over moles per Kelvin. And then our temperature needs to be in Kelvin, so we add 273 to the 20 degrees Celsius, and we get 293 kelvins. And so if kelvins is on top, let's do all the crossing out here. We got kelvins. Moles is moles per liter, so the opposite of that is liters per moles, and we're left with bars. So if we do the psi S and we multiply this all out, it's going to be a negative 2.4. So hopefully you guys got that. And if I have negative 2.4 outside the cell, it should be real easy to tell which way the water is going to move in. And so the water will actually move into the cell because this is a lower negative number, or the cell has a lower water potential. If we took that same cell, which I believe was negative 3.3, and we put that into a solution full of salt, the psi S would change just a little bit. It would still be negative, but this time, because it's salt, it dissociates into 2 particles, and unlike sucrose. And so because it dissociates into 2 particles, we have to put a 2 there. And then we have the same thing, because if its solution in question 4 contained 1 molar, 0.1 molar, NaCl instead of 0.1 sucrose, what is the psi of the solution and what would the direction of the water be? So we just say the same thing, 0.0831 liters per bars over moles per Kelvin, and then this would still be 293 Kelvin, which I got from adding the 20 degrees Celsius plus the 293 for the conversion, and the psi S would equal a negative 4.9, and then 4.9 negative. And so where would the water flow? Well, negative 4.9 is lower, and so the water would move out of the cell in all directions there. Now, it's going to be hard to recognize, but these next problems, you're going to need to split it up into two parts. And so what I like to do is think about what's inside the cell and what's inside the beaker. And so we'll do up top, we'll do the cell, and what's below, we'll say it's the beaker. And I'll indicate that by saying the psi of the solution inside the beaker or the psi that's inside the cell. And that's just how I like to keep it separate. And it tells me that a plant cell with a psi S of negative 7.5 bars is kept at volume when immersed in an open beaker that has a solution of psi S of negative 4 bars. So what is the cell's, it should say psi P. So what is the cell's psi P? Oh, it says it right here. So what is the cell's psi P? Apparently I'm blind today. What is the cell's psi P? So to do this, what I like to do is usually start with something that's easier. And the reason that I know that the beaker is going to be the easiest one is because it's kept in an open beaker. And if you remember from our third or fourth problem, the open beaker means that the psi P is going to be equal to 0. So if you can remember that, that's going to be really helpful. And so to find the total psi of the beaker, you got to have the psi S and the psi P. But since we already have both of these, it makes it really easy. So we have negative 4 plus 0. And so the psi B is going to be equal to negative 4. So we already know that the negative 4 is outside of the cell. Oh, and I guess this is a plant cell as well. So let's put a little cell wall around it. So we know that the beaker is a negative 4 psi. Now we need to figure out what the cell is. Well, it tells us that the plant's cell has a psi solute of negative 7.5. So our psi of the cell is going to be equal to negative 7.5 plus psi P. And we got to find out what psi P is. So that means that there should already be some way to figure out the psi of the cell. Well, let's read back in here in this question. If it's kept at a constant volume when immersed in an open beaker of a solution that's different, that's going to mean that the molecules are in an isotonic solution. So that must mean that if we go back to number 3 in this video, that if they're staying at a constant volume, that they're at equal water potentials. And so if they're at equal water potentials, then, or if they're at equilibrium or anything else like that, our psi C is going to be equal to the psi of the beaker. And so that's going to be negative 4. And so if our psi C is negative 4, we can make that equation balance to negative 7.5 plus the psi P. And so if I add over the 7.5 plus 7.5, I'm going to get a psi p equal to 3.5. Okay? So this kind of got moved over to here. I should do the beaker on top next time. So this will get moved over into here, and psi p will be equal to 3.5. Since this is already out, we already know what the total psi is. Okay? So how do I know that I'm correct? Well, if I put this equation together, it's going to be negative 4 equaling negative 7.5 plus 3.5. And if I take that negative 7.5 and add it to 3.5, negative 4 and negative 4 should be your outcome. And so this is a way to double check, and you should do this every time because each one of these counts, is to double check your answer and to make sure that it's correct. Let's give you a couple more just to get familiar with it. Alright, so if I am going to split this up, say the beaker's here, and the cell's here. This might take 2 frames. What we're going to do is we're going to have, at 20 degrees Celsius, a cell containing 0.6 glucose is in equilibrium with its surrounding solution containing 5.5 molar glucose in an open container. What is the cell psi p of the cell? So I'm going to leave this open because it's going to be a little bit more work. So let's look at the psi of the beaker and the psi s of the beaker. Let's look at the psi s of the beaker and the psi s of the cell. Well, we know that they're both containing glucose, so that's going to be a negative 1. And that's going to be the same for both of them because they're both dealing with glucose. Our concentration, though, is a little bit different. Inside the beaker, in an open container, it's 0.5 moles. And in here, it's 0.6 moles. And so we can just add in our constant, which is 0.0831, 0.0831. And the last thing is temperature. It's at 20 degrees Celsius, so I add that to 273, so I get 293 kelvins. And over here I get 293 kelvins. Okay? Do all of the math. My psi s is going to be equal to, inside the beaker, of being negative 12.2, and the psi s inside the cell is going to be negative 14.6. Alright, so inside the beaker, well, we have this open container. This open container means that our psi p is 0. So our psi of the beaker is going to be equal to negative 12.2. So we have the psi of the beaker of being negative 112.2. Hopefully you can see that. And our psi of the cell, we still don't know. But if the psi at the psi of the beaker and the psi of the cell are at equilibrium, remember water's moving in and out at the same time, we need to figure out that the psi of the cell has got to be equal to that. So we got to know that it's negative 12.2. And so if we know that, Negative 12.2 is our total psi. That's going to be equal to negative 14.6 plus our psi, of our p. And that's what we're going to try and find. So we'll add 14.6, add 14.6, because what I do to one side I got to do to the other. And that's going to equal our psi p. And if we do that math correct, that should be negative 2.4. And if these are equal, we got to take the negative 12.2, equate that to the negative 14.6 plus the psi of the p. And if we do that, we need to get this over on this side, so we can put psi p. And then to get this 12.2 over to the other side, you just add 12.2, add 12.2, and so our psi p is going to be equal to negative 2.4. And then if we add, and then our cell is negative 2.4. To double check your answer, you have 14. To double check your answer, you have negative 14. To double check your answer, you have negative 14.6 minus 2.4, or plus a negative 2.4, so you can think of it either way. And that's going to be negative 12.2. So remember, when dealing with water potential, if it's at equilibrium, water's moving in and out, and the potential for water will be the same inside and outside of the cell. You can use that to your advantage to help you with some of these problems. Thank you for watching Moreauknows. Now you do.